Hello and good morning. Welcome to AIST's Decarbonization webinar on today, Wednesday, the 8th of October. My name is Charlie Bender, and I'm joined by a host of presenters and moderators for this season's 2025 Decarbonization webinar series. Today's topic is pressure to perform, unlocking energy savings in steelmaking with efficient and reliable compressed air systems. We want to first take a moment to thank our sponsor, Universal Compressed Air, and they are supplying not only the presentation, but both a moderator and presenter. So thank you very much for this sponsorship. AIST webinar guidelines are pretty straightforward. If you attended before, each of you in the audience has been disabled from an audio standpoint. All questions should be sent through the Q&A feature was at the bottom of your screen. It may be a yellow tab. But submit your question, and those questions will be determined during the presentation whether they're answered by the presenter in person or if we make contact after the presentation where you can continue to receive your answer. This session is being recorded and will be available for replay demand on AIST's website. We ask that no photos or recording of this presentation and come back to the AIST website for that version. If you're experiencing technical difficulties, please use the email address training@aist.org to receive technical assistance. AIST has two guiding antitrust and anti-harassment guidelines. If you're not familiar with them, the information indicates do not participate in price fixing for the antitrust and make each of our meetings a comfortable meeting for all attendees. Again, the Q&A feature of this Zoom software is where you submit your questions anytime. Our moderators will help the presenters answer as many as possible during the presentation. Previous decarbonization webinars have included a host of information, and they're in the line all the way back to 2019, I believe. At this point, I'd like to turn the presentation over to Joe Mori, who is Vice Chair of the Decarbonization Subcommittee of the Energy and Utilities Technical Committee, and Joe has a few words to share with us. Joe?
Hi, good morning. My name is Joe Mori. I'm the Vice Chair of the AIST Decarbonization Subcommittee of the Energy and Utilities Committee, a technical committee. Our goal is to support the various technical committees of the AIST and the broader steel community as they make this difficult sustainability journey. We hope you will enjoy today's presentation. Thank you.
At this point, I'd like to introduce both moderators, Pollyanna Araujo and Tim Sohnlein. Pollyanna has an extensive background as a principal process engineer currently with WSP's energy, resource, and industry sector, and is a licensed professional engineer in Ontario, Canada. She has worked with electric arc furnace operations, focusing on process optimization, including burner profiles to improve thermal efficiency and reduce operational costs. Her experience extends to blast furnace operations, where she has worked with both charcoal and coke-based iron-making processes, optimizing, reducing agent ratios for maximum efficiency. Tim is a global director at Universal Compressed Air, and he has over 30 years of experience with compressed air systems, applications, and compressor technology. He has a specific focus in steel production processes that utilize compressed air, and he is an innovative industry leader and a key contributor with respect to energy optimization, compressed air system design, and equipment reliability. I'd like our moderators now to introduce our presenters.
Wendy Dimino is a director at Universal Compressed Air. She has a Bachelor of Science in Mechanical Engineering. Her technical specialty is in turbo machinery, Wendy has spent over 20 years in manufacturing, design, and global applications of compressors and compressed air systems. In addition, she has focused on plant-wide compressed air system optimization, reliability improvements, and overall cost savings in steel production applications. Her experience in both EAF and integrated mills lends to a depth of specific knowledge in compressed air applications and opportunities to be uncovered. She is a proponent of sharing her knowledge and enabling mills to optimize their production processes.
Good morning. Alton Stokes is a key contributor in the compressed air industry. He has spent his entire career, over 35 years, optimizing efficiencies and improving the reliability of compressed air systems. He is the Vice President and General Manager of AIST System, which concentrates on compressed air, vacuum, and water reliability and energy efficiency. AIST also engineers, designs, and manufactures local controls, automation, and SCADA platforms to manage these systems efficiently. He specializes in compressed air design and demand-side system application. Combined with his experience, Alton is on the forefront of new technology and is a proponent of continual education. He regularly presents educational workshops and webinars on compressed air reliability and efficiency.
Our first presenter will now share slides.
Thank you. Thank you, Charlie. I also want to thank the Decarbonization Committee for providing this platform and all the attendees for their time today. Today, we will be reviewing easy opportunities for energy reduction and reliability improvements for optimizing compressed air systems. Why are we here today? We're going to go over reasons why you would want to look at the compressed air systems for overall reduction of cost of operation and overall reduction of the kW contributing to the compressed air system. Compressed air is critical to the steelmaking process in many ways. It's also a very expensive utility. The electric drive motors on compressors consume up to 20% of the plant's electricity. There's many opportunities to reduce the system power by up to 40%. In addition to that, there's opportunities to reduce the total cost of ownership by up to 50%. Compressors in general are very inefficient. Most of the input power is rejected in the form of heat. As you can see with this chart, of the input power, 80% is lost due to heat of compression. So that's the inefficiency of the process. The compressor also has mechanical losses, which contribute to about 5%. And of the useful output of each compressor, only 15% is dedicated to the process. And of that 15%, 50% is wasted through inappropriate uses of compressed air and compressed air leaks. So the bottom line is about 7.5% of the input energy is actually used with purpose. We're going to look at the importance of compressed air in steel mills. We mentioned that compressed air is critical for the applications of steelmaking and process uptime. The goal today is to give you the knowledge of where to find the opportunities to improve the system efficiency and where are those opportunities in the mill. So you can find them where compressed air is being used, and that's for conveying applications, pneumatic tools and valves, machines and door actuators, also the furnace door actuation, air mist systems, instrument air, carbon and lime injection for the electric arc furnace, cooling, bag houses, burners, lances, ladle cars, etc. So there's many applications, and we'll go through applications for both integrated mills and electric arc furnaces in this presentation. So the importance of compressed air in the electric arc furnace is that clean, dry air is used to inject carbon and lime to the slag through lances. And the end goal of this is to create a perfect, foamy, fluffy slag. And that is extremely important for the yield rate and the process of the electric arc furnace. So compressed air delivers those particles into the slag, and the compressed air should be clean and dry. And what we mean by that is clean, which means there's no oil carryover, no oil in the compressed air. And dry means that there's no moisture content. It's typically -40 degrees Fahrenheit for the pressure dew point of the compressed air that's needed for this process. So to maintain that constant feed rate of the carbon and lime particles, you need to have no moisture content in that compressed air. Otherwise, it begins to clump and it blocks the lances, and then that leads to production slowdowns and work slowdowns, and then they need to perform maintenance on those lances. You also need a consistent pressure delivered with that compressed air, and that drives the carbon and lime particles deep enough into the slag for a proper chemical reaction. And that chemical reaction is extremely important, and in turn, it yields a higher yield rate and better quality steel. With this proper slag, you get energy savings, reduced energy demand, and it also contributes to a longer lifespan for key components such as the electrodes and the refractory life. So the compressed air, being clean, dry, and of high reliable quality, has a high impact on the melt shop operations and profitability. So the yield improvement is the largest cost benefit to the electric arc furnace. So linking that metallurgy to profitability and sustainability are factors that improve both the financial performance of the melt shop, and it leads to the decarbonization goals being increased. This is an ideal compressed air system. So there are compressors, a bank of compressors on the right, and a bank of heated compression dryers on the left. So just as steel mills own and operate compressors and equipment associated with the compressed air system, Universal Compressed Air, we design, build, own, and operate complete compressed air systems. They're designed with the highest efficiency and the lowest total cost of ownership, and deliver contractually guaranteed clean, dry air to the customer. With that, the compressed air system components consist of two sides. We have the supply side and the demand side. The supply side consists of the compressors, air drying equipment, filtration, receiver tanks. That goes to a header, and that's connected to distribution piping that goes to all the end user applications on the demand side. When you walk through the mill, you typically find three different types of compressors. We have rotary screw style compressors, we have reciprocating, and centrifugal compressors. They're all good for different applications, different flow ranges. Some are oil flooded, such as the rotary screw in most applications. In the reciprocating, that means that there's oil in the compression chamber, and that gets filtered and delivered to the process. With the centrifugal, that is oil-free by design, so there's no oil carryover in the process air. As far as energy savings opportunities, what we want to communicate to you today, that there's two different parallel avenues to go about this. You can produce air more efficiently, and that applies to the supply side. And you can also use less compressed air, and that's on the demand side. Here are several ideas to apply for each of these applications. As far as the supply side, first and foremost, you can improve the compressor control system. You can upgrade the local controllers and also add a master controller if you have a fleet of compressors to operate the team of compressors more efficiently for the demand profile. You can add heat recovery applications. Predictive and preventative maintenance is key for peak efficiency performance and also for peak reliability. You can look at optimizing your discharge pressure and your dew points, and look at compressed air storage strategies. As far as using less air, this is reducing the power input for your system to deliver the same amount of flow that's required for your process. So what you can do here is target leaks and repair them, eliminate inappropriate uses of compressed air, look at reducing the system pressure, looking at using low pressure air where high pressure compressed air is used for certain applications that don't need the high pressure air. And for condensate drains and dryers, they operate in two different modes. One mode is a timed mode, and another mode can be a demand mode. If you select the demand mode option, you're definitely going to save dollars, and you're going to save compressed air, and you're going to save power. Maintenance is a key factor to success, and that's in the performance, and that's the efficiency, and that's the reliability of the system. I would say with this slide, there's there's three main takeaways here. First and foremost, I'd like to focus on the inlet filtration. This is easy to schedule maintenance for the filters. Look at the delta P, the differential pressure across the filters. I would highly suggest using the OEM branded filters for each particular compressor. They are designed with the purpose to protect the compressor. So these filters are designed with two stages. Typically, they're designed with a specific media and a specific micron filtration level, and they're designed with a certain number of pleats per inch. So that protects the compressor. And here's an example, poor filtration. We have a brand new impeller here, and you see the corners are squared off of the inducer area of the impeller, which is downstream of the inlet filter. After time of poor filtration, you're essentially sandblasting the impeller, and the edges become rounded out. And when this happens, the compressor loses efficiency. In addition to that, another key component for maintenance to improve reliability and reduce power is cooler maintenance. We have a clean water and tube style cooler here. If you don't have good cooling water quality, what's going to happen? You're going to get scaling, you're going to get fouling and sediment in the tubes. And again, the coolers are not going to be able to perform how they were designed to perform. And the essence of this performance degradation is an example where we would have a 1,000 horsepower compressor, should deliver about 5,000 CFM of compressed air. When you have this degradation happening, that 1,000 horsepower compressor may only be able to deliver 3,500 CFM or maybe 4,000 CFM. So you see, essentially, you would have to turn on another compressor, use more power to deliver the same amount of flow to your process. So these are some key contributors to optimizing the system with performance and reliability. And last but not least here, the third takeaway to this slide would be quarterly oil sampling. The oil and the lubrication protect the rotating components and the gearing inside the gearbox. And you'd like to look for maintaining, eliminating particulate and maintaining certain viscosities. So those three maintenance practices will provide an efficient system that's reliable. Some more pictures to just show how the impact of maintenance and performance, power, and reliability is this compressor. It was brand new. And after calling on this customer and looking at the compressor room and seeing non-OEM filters, seeing filters in the inlet housing that were plugged, could be, excuse me, could be changed and maintained on a more regular basis. We opened up the machine and we had the opportunity to look what was happening and what the effect of poor maintenance was on this machine. So this machine that would last typically 30 to 40 years of lifespan, after 2 years, all the internal air passages were coated with dirt and debris. The impeller was coated with dirt and debris. You can see this in the enlargement here of the impeller blade. It's rounded out, so it's begun to lose efficiency. And then in addition to that, there's a risk of reliability associated with this. With the face of the impeller covered in dirt and debris, that could enable this piece to vibrate. And after a certain level of vibration, there could be metal to metal contact between these two components as the impeller spins approximately 70,000 RPM. When you have metal to metal contact, you would have a failure. In turn, that would lead to purchasing expensive rotating components to replace these. And those expensive components also have a long lead time. So in conjunction with that, you'd have to bring in rental compressors and also utilize spare compressors if you do have them on site. So the point is, a small maintenance function can lead to a lot of detriment or a lot of success within the system. I think pictures go a long way, and the goal here is to let you understand where to look for these opportunities in the mill. So proper predictive maintenance will 100% reduce your total cost of ownership of the system, and it will 100% improve the reliability. So some things to look for, more filters. These are on motors. These need to be changed. Also, there is filters on the mezzanine that needed to be changed also. This machine was down for an overhaul. This should have been properly covered to eliminate any contaminants from the ambient air being ingested in this compressor. And over here we have oil leaks in the compressor tubing, and those could be fixed for safety purposes. Filtration is one of the biggest components that we find that could be maintained better and alleviate issues with performance and reduce the power consumption of the system and improve reliability. So these filters here were so clogged with dust and dirt and debris, they were actually bending the metal frame of the elements. And what's interesting about this picture in the middle is that the new elements were sitting right on top of the compressor. So they were just in need of attention. So a proper maintenance program that's scheduled with spare parts on hand goes a long way for reliability and reduction in power. We talked about waste heat recovery. There's 3 ways to go about this for a compressed air system. If you do have an air-cooled compressor, you can look at ducting the cooling air to heat a building or a room. For water-cooled compressors, you can take the rise off that water manifold and preheat water for boilers or HVAC systems. And in regard to dryers, I would say about 95% of compressors have a desiccant dryer following them in these steel mill applications. And installing a heated compression dryer, I think, will in turn give you the quickest ROI and capture that wasted heat and using it in a purposeful way. Other dryers that we see installed after compressors are blower purge style or heatless style. And those dryers take up to 15% of compressed air that was generated, and they dry the desiccant beds with it, which in turn dries the process air. So the biggest bang for your buck essentially would be to install a heated compression dryer for these applications, which requires basically no cost for operation, as it's using the waste heat from the compressor to dry the desiccant. And if you don't know where else to start by collecting the information. It's a good process to understand what's installed and how it's operating. So a lot of customers do not understand or have the data assessed to understand how much they're spending on their compressed air system and where they're spending their money. And that will reveal opportunities in areas for improvement. So first, you want to catalog your equipment, look at all the nameplates in your mill, as far as compressors, flows, powers, dryers, purge air. Identify what your mill is paying for power. Understand how much you're paying for maintenance of the compressors, maintenance for dryers, cooling water costs, spare parts, rental compressor costs, any labor costs, and tally up that cost and understand what the full picture is. And then you can look at how much you're spending and where are you spending that money. And that will reveal opportunities for areas of improvement. This picture on the left graphically represents that about 75% of the cost of ownership of this compressed air is spent in power. That is ideal. This is typically not the case when we data log all the information from a mill. We find where maintenance and rental compressors may be the largest cost of their compressed air system. So then they can start to fine tune and address the areas for improvement and realize power savings and cost savings. But really we want to see people measuring what they manage and understanding a baseline. This is my last slide here, and I had a mentor in the steel industry, and he was in the steel industry for over 50 years, and he ended a lot of presentations with this information. So there's 4 factors to achieve progress and to go about achieving your goals. 1 is time, 2 is people, 3 is money, and last but not least is the desire and motivation to drive these projects. And that concludes my presentation. Thank you.
Thank you, Wendy. We have a couple of questions from the attendees. I'm going to read the first one. So what new HSE-driven innovations have emerged for reducing compressor noise, enhancing real-time monitoring of compressed air systems, and mitigating water condensation in distribution lines?
Could you repeat the first part of that question, please?
What new HSE-driven innovations have emerged for reducing compressor noise, enhancing real-time monitoring of compressed air systems, and mitigating water condensation in distribution lines?
Okay, that's a great question. As far as monitoring the compressor data, there's advanced control systems that control the compressor more efficiently, and those vary depending on the type of compressor that you have. There are control systems for centrifugal compressors that essentially optimize the machine performance depending on the temperature of the ambient air and cooling water. And it could optimize performance by allowing it to have a better turn down rate based on the cooler temperatures and take advantage of that single unit operating on that demand versus having another compressor click on. As far as moisture in the condensate lines, I believe heated compression technology, applying that to the drier portion of the system has a huge advantage for power and cost savings. I would say measuring and monitoring that dew point. We find a lot of dryers are operating maybe at a higher dew point that they need, or the dew point is plus 30 when it should be minus 40. And comments that I've heard is, when we turn on the compressed air for certain processes, it's like a garden hose and water comes out. So I feel like measuring what you manage and monitoring the system will help that process.
Thank you. One more question. So, given some older steel plants are over 60 years old, how often do compressors need maintenance inspections, upgrades, eventual total replacement?
So as far as inspection, I would review the compressor data every day as far as the data points and understand what's normal and what is an indicator to premature failure or indicator to maintenance that needs to be performed. If compressors are properly maintained, they can last up to 60 years, depending on the technology, and we see them still installed. So I think overhauls, as far as inspection to the gear case, I would say that's not necessary unless you have indicators telling you that there's an issue, and that's from the data, pressures, temperatures, cooling water, cooler delta T's, approach temperatures that you would monitor. And as far as end of life, I would say when the compressor is not performing per its specification, or there is reliability issues where it's causing outages in the steel mill process, you would look at upgrading that compressor or replacing it.
Great, thank you. So on the second to last slide, what was the difference between the two graphs?
The first graph showed, I can share my screen again. This graph shows an ideal compressor system. So all the costs that contributed to the compressed air system were tallied up and input, and then they were showed where most of the spend was. An ideal compressed air system, 75% of the spend should be in power. The remainder should be in equipment and maintenance. So if you're spending more than 50% of your system cost in maintenance and rental compressors, there's an issue where something needs to be addressed and can be optimized. And that optimization will directly relate to reliability and reduction of power. And what you want when you have a reliable system and you want to be proactive versus reactive, when you have that, you're going to get consistent monthly spend and you're going to get consistent monthly reliability. And those go hand in hand.
I don't know if we still have time for a couple more questions, but there are many questions here. Is there enough excess heat to apply an organic Rankine cycle system to produce electricity?
I would say we would calculate each compressor based on the horsepower. So basically, if you take the horsepower of the machine times 2545, and that gets you your BTU per hour, and then you can look at the heat rejection rate of that compressor. There's ambient air, there's cooling air, and there's cooling water for each application. So based on the horsepower, you can calculate the BTU per hour that needs to be applied to other processes. And if that meets the requirement for the cycle, then you can look at an application to use it.
Okay, thank you, Wendy.
You're welcome.
Okay, good morning. Can everybody see my screen?
Yes,
Hope so.
looks good.
All right, thanks. All right, let's get started. I'm Alton Stokes with Case IZ Systems, as Tim introduced me. We're going to talk a little bit about the demand side applications this morning and just kind of want to highlight a few things that Wendy went over. Compressed air is considered industry's fourth utility, and it's really one of the only utilities that's produced and managed by the end user. It's very inefficient, as we talked about, and most of the time there's no cost assigned to it. So there's really no known cost associated with it. So there's no penalty for using it. Ask yourself this question, what's your efficiency of your boiler system? I've heard 80 to 90% is pretty good. Cooling towers and chillers have a efficiency of 80+% normally, and your power factor at your plant is normally in the 90 to 95% range. But when you deal with compressed air, it takes to get 1 horsepower of air motor energy, it requires 7 to 8 horsepower at the air compressor shaft. And as we mentioned before, that's less than 15% efficiency when using compressed air. And that's if you're doing everything perfect. 80% of the electricity input goes to heat, and we can recapture that, utilize it to heat other processes or use it in other energy recovery systems. Most of the opportunity is not in the compressor room. Wendy spent a lot of time on the energy input side and how to make that better, but it really only represents about 1/3 of the opportunity. And as we mentioned earlier, the controlling of the pressure and coordinating of the compressor controls is a big part of that. But most of the opportunity is out in the mill. And through our work over the past 30 years, we were part of the lead DOE technical team for the Compressed Air Challenge. We noticed that the opportunity out in the mills had a much lower capital cost to correct and had an immediate impact on the production process. So we're going to spend some time looking at that this morning. You need to make sure that in the compressor room that we are controlling the compressors efficiently. They need to be equipped with some type of auto start and stop functionality, which allows the compressors to turn off rather than run part loaded or blow off. This can be done with automation. It can be done with staggering set points. Smaller systems, you can use the onboard OEM microprocessors and coordinate those together. But we got to make sure we are controlling the compressors so when the demand's not there, we're able to part load them and then shut them off when they're not needed. As we discussed earlier, 50% of all the compressed air that is produced goes to waste. And it really falls into 3 buckets: inappropriate users, artificial demand, and leaks. And we're going to talk about each one of those just for a minute. Air leaks, that's the favorite child to talk about. They're easy to identify. Typically make up 20 to 30% of the total compressed air consumption in a plant. Most of these are found at the point of use where your joints and flanges go down to a regulator or hoses or tubing, polytubing, and it's really inside the machine or near the application of the air. Very rarely do we find 6-inch, 12-inch pipes leaking, and in those cases, it takes a mill shutdown. You have to do that on an outage. They're reoccurring, so you have to spend time, a couple times a year doing some type of leak detection and identifying those and repairing them. And most plants of any size have invested in a leak detector and have some sort of plan with their employees to tag these and get them repaired on a routine basis. The second area of opportunity is eliminating artificial demand. Artificial demand is the additional consumption of the system due to running the system pressure higher than is required. Every 2 psi that we raise the header pressure is a direct 1% result in power required to get that pressure up. And the higher pressure creates more leaks. What's ideal pressure is important. You've got to measure and get data on what the article pressure at the point of use is and try to control your header to that pressure. Lots of pressure drop through the system. Most people think it's in the piping and distribution system, but typically it's through dryers and filters and point of use components that are undersized. And one of the things you can do is utilize storage throughout the system to reduce the pressure drop from the air moving through the piping system. And we'll talk about that a little bit in the next few slides. Here's a typical pressure profile when we send out our engineering team to do an audit. What we find typically on the left side is a pressure range for the compressors to operate in. And in this example, we're using 100 to 110 psi. The compressors will operate. And then you have some pressure drop across dryers and filters. If you've got pre-filter and after filter and desiccant style dryers, very common to see 5 to 10 psi pressure drop across those as filters get fouled and the desiccant beads get loaded up with moisture. And then this line going across represents the header pressure throughout the mill. And you'll see how this line droops here. I get a lot of feedback that I've got a spell check issue here, but that system droop, it is droop, it's not drop. As the air is distributed through the plant, there's people taking air off the header as you go out further and further away from the compressor room. And it caused the system to droop. And you can never get that droop recovered no matter what size pipe you run. It's just a lack of storage near the application causes the pressure to droop. And then what we find when we measure, and measuring is very important, data is king. At the point of use, we'll set a regulator for 80 or 85 psi. And then when that device needs air and it actuates, the lack of storage or the hose or pipe downstream of the regulator doesn't have enough capacitance to fill the void. When that regulator opens, the pressure drops. And it's very common to see 30 pounds of drop downstream of a regulator or an FRL at a point of use. And the actual work is being done down here at 50, 60, 70 psi. And you don't know that until you put high-speed data loggers in. And part of our exercise when we come on site is to do that. We map this pressure profile. Where are we at in the compressor room? What's the pressure droop through the system? And then what's the article pressure that we're actually using it at? And then we modify and correct these issues so that we're able to lower the pressure. And by lowering the pressure out here, we get rid of this pressure drop. We can lower the pressure back at the compressors, and we're saving 1% energy for every 2 psi we can reduce that. And when we're fixing these issues at the point of use, these are very low capital dollars. It's upsizing hoses, it's adding small storage tanks, very, very inexpensive to correct. The third pie of that chart for waste is inappropriate users. And this is just a sample of one of our audit reports that spelled out a few applications that showed where all the waste was going. And in this system, this is a small steel foundry, only producing about 6,000 CFM. But as you can see here, as we look at the items, air-driven bin vibrators, cabinet coolers, some open blowing. They had a lot of open blowing on the process side. As we corrected this and got rid of some artificial demand and leaks, about half of this 6,000 CFM was waste. In this instance, it was 43%. So it's very common to find this, especially in heavy industrial manufacturing like steel mills. Some of those users, inappropriate users, are air horns, cabinet cooling, vacuum generation, any open blowing that's unregulated. Air motors need to be, retrofitted with electric motors. And then as we can lower the pressure on these applications, we can use, fans or blowers with high volume air and low pressure and do the same effect as we can with a little bit of compressed air to higher pressure. We can use electric vacuum pumps, electric motors, and engineered nozzles to correct these. And these pictures are very typical in your industry, where to the left here we have a lot of little flexible tubing blowing compressed air on the process. Show leak, a leak survey going on here on the left. Some makeshift engineered nozzles on between rollers on a steel mill. We've got an air horn here, very common to evacuate air or put air into a area that needs cooling or evacuating of exhaust or fumes. And then to the right is just an example of a hose that was leaking sitting there. Nobody had used it. It was just laying there leaking. Everybody walking by, ignoring it. One of the things that you can utilize is storage and eliminating peak demands. And peak demands is what helps drive the overall cost of energy. Most people have hot standbys. They've got compressors running either part loaded or in blow off. So when a peak demand hits, they can support the system. You can do the same thing with storage. There's several lists here of applications. The control storage I'm referring to is in the compressor room. Storage provides time. So if we can store air in the compressor room at a few PSI higher than we actually needed in the header, and we can separate the supply system from the demand system with the pressure flow control valve, we can utilize that control storage to meter out to the plant and keep the pressure steady versus keeping a compressor in hot standby, blowing off. We can use storage to handle those peak demands. Some of the peak demands that you see, any kind of dense phase or dilute phase transportation, we can use dedicated storage there with meter recovery, and I'll kind of show you an application using that. Obviously, lances and blowguns are large users that create peak events. You can use storage there, or better yet, we can lower the pressure at those applications and use a better type of lance. Most of that work can be done at 30 to 40 PSI, so regulating that helps. Also can put storage and regulation at diaphragm pumps, so we control the speed so we don't run away. The diaphragms don't run away when the product's not there. And then any high pressure intermittent applications, dedicated storage can eliminate those peaks and help the overall demand just be averaged out. So here's a very common application in steel industry. It's a dust collector or bag house. And this is a typical setup. You have a 2-inch line, on a large bag house with a filter and a regulator, feeding a manifold that's most of the time 4 to 6 inches on a nice size header, and then it pulses on a timer. And what you'll notice on the next slide is when we put a high-speed data logger in, we're recording the pressure on that manifold at 25 times per second. And then we build a profile and watch the MAC valve open to reverse pulse that baghouse. And as you can see in the orange line here, the header pressure is in the 92, 93 PSI range up here. And these dips in pressure down to 60 PSI is when that valve opens and fires the air to knock the cake off the bag. When you measure this, it's only 8 cubic feet per pulse. However, due to how fast this rate of change is here and the pulse duration, it creates a 1200 CFM rate of flow event. And that event affects the entire header. It causes that droop that I showed you in a previous slide. And once the system gets into that droop, it can't recover. So one way to solve this is to retrofit the baghouse with 3 or 4 key components if you don't have them. One is downstream of the filter and regulator, install a check valve. This provides a dedicated storage application. Put in a needle valve. This can be a 2-inch gate valve of some sort, somewhere where you can really dial in the flow. And then downstream of that needle valve, just simply tee in a small tank, and we can help, calculate the size of this. It's just a math problem. But once we do that, now when this valve actuates, the pressure in this tank falls just like it did before, but it only falls, 10 or 15 pounds instead of 30. The needle valve we set so that the airflow through that needle valve simply fills this tank up very slowly back to the pressure desired right before the next valve fires. And the check valve keeps the air in that receiver so the rest of the system doesn't steal it. So this 6 CFM pulse that we mentioned before, instead of it being a 1200 CFM event, the header sees it as just a small 36 CFM event all the time, and the large peak event is coming out of this storage, and the header never sees the dust collector of the baghouse fire. That helps that droop. None of this is possible without data. So this is just a generic screen of data from a compressor room and a compressed air station, cooling water information, dryers, compressors. We've got power, we've got temperatures, flow, dew points. The point of this is if you don't measure it and you don't monitor it, it's very, very difficult to manage it. And because compressed air is dynamic, things are always changing, not only in the compressor equipment, but out in the demand side. So creating a baseline is very important. Part of what we do is come out and spend a week or two on site and install data logging equipment. We can utilize some of your data that you're collecting, and we create that baseline for you. We create, a process flow diagram that shows how your system's laid out. That helps, give you a picture of what's there. And then we analyze the production applications that drive the system issues, dust collection, testing. We go out to point of use to see what the article pressure is at some of the critical applications. And we typically ask, if we failed a compressor today and the pressure started falling, what's the first department that calls? And we want to go spend time with that person in that department to find out why the pressure is so critical in that area. And typically storage or fixing the point of use pressure drop, we can correct that so they're not the first one to call anymore. And part of that effort, we propose a process flow diagram of all the corrective actions. We put a detailed plan of action together with cost and financial impacts, and then we provide a full report to the customer so they can correct those issues and develop a project. And all of our work, when we do this, is projecting a return on investment, and we guarantee that investment based on our findings. So just a little highlight of what we talked about. We need to stabilize the pressure, which allows us to lower the pressure in the plant, and that saves energy. We need to eliminate the pressure drop out in the plant. Providing dedicated storage helps with that. It helps eliminate the peak events. It helps eliminate that pressure differential across those components. And normally, when you eliminate waste, it's easy. You know, fixing leaks is easy. Putting electric vibrators in or electric motors over air motors is easy. You just gotta, you gotta want to do it, and you may take a little bit of engineering to do that. And then putting a good leak program in is something that'll help maintain the leak load in your plant. So remember, compressed air is not efficient. If there's any way to do anything in your plant not using compressed air, it's worth at least looking into. Small changes can help the efficiency. 2 psi equals 1% energy. So if someone asks you to raise the pressure, it's going to cost you. So let's keep driving the pressure down to save energy. Reducing the temperature will also help. Every 10 degrees is about 2% of wasted energy. So the compressor room temperature is important. Proper ventilation helps. Remember that leaks is about 20 to 30%. So make sure we get a leak program in place. And then the temperature discharge, which comes right as a result of the cooling water, it drives up the temperature discharge, which doubles the moisture going to the plant or to the cleanup equipment. And that's my last slide. Any questions?
Yeah, and this is Tim. We got a few questions here for you. The first one is, after leaks are identified, what is the best way to target repairs without disrupting production?
Yeah, most of that leak load is in the point of use applications. What I've seen in the past is, every mill has certain down days, either half a day, a month in those departments. You tag them, and then, you attack them while they're down in those departments. The mill-wide shutdown stuff would be when you have a 6 or 8 inch header that's leaking. That's going to have to be planned, on a cold outage. But most of that can be done on a day outage, in certain departments.
Great. I have another question here. How do I justify the instruments and data to accounting for if I don't already have this information? And then how do I determine where in the plant is the best place to get data?
Yeah. To justify anything, we've got to use energy or reliability, and that is a direct impact to the cost of compressed air. You've got, most of the time, you need an audit done or somebody to baseline the information using portable data loggers to show the value of the information and where the cost and waste is going. Once that happens, part of the project going forward would be continuous monitoring. So it's not very difficult. Instrumentation, if we're doing an automation system in a plant of significant size, the automation part's a large investment, but the instrumentation is not significant in the grand scheme of things.
Great. I have another question here as well. Does the Department of Energy or local utilities get involved in helping or have any programs to reduce leak rates for compressed air?
Yes, there's most utilities have 1 or 2 types of incentive programs. Compressed air normally falls under the custom program when you want to retrofit the system. But some utilities also have a leak and fix program, depending on where you're at in the country. We're very familiar with all those programs, but there is incentives and rebate money from the utilities to not only do the leak audit, but to fix them and to do the overall audit to, retrofit a system.
Great. And I've got one last question for you here. What is a good method to control leaks once they are targeted and repaired?
I mentioned earlier, keeping the header pressure low. A pressure flow control valve, which is a butterfly valve that's controlled with a PID loop to separate the production side from the supply side. That helps those leaks as you fix them, and we can lower the pressure because the demand's gone away. That'll keep that leak rate, under control. You're still going to have leaks, but they're not going to be leaking at a higher pressure because you've set the header with a flow controller.
Great. And we've got one more that just popped in here, Alton. How can we
Okay.
reduce compressed air temperature to get better dew point going to the desiccant dryer?
It's all about your coolers. If they're air cooled, you need to, keep the coolers clean by blowing them out, pressure washing them out. If they're water cooled machines, you need to treat your water. You need to rot out your coolers. The discharge temperature of the compressor is, directly affected by the coolers. If you can't do that and you've got high temperature water, or you're in a hot and ambient air, air cooled machines, you can put a trim cooler in and use either chilled water or cooling water to run across that cooler to get the temperature down prior to the dryers.
Thank you, Alton. That's all the questions we have right now.
Thank you, Alton and Wendy. We're going to wrap up the presentation with a little information on where to find the recording. Not only the additional webinars, but past webinars are located on this portion of the AIST website. There is a second part of the website under Technology Committees that will take you directly to a curated YouTube playlist of just the decarbonization webinars. We want to highlight that the parent organization, the technical committee called Energy and Utilities, has an annual Energy Achievement Award, which relates significant savings due to energy reduction projects, and its nomination system is open until June of every year, with the award the following year. AIST also has more than 10,000 technical papers in a resource center available for download. We want to highlight the in-person conferences and training seminars that are occurring between now and Thanksgiving in various cities. And remind everyone that the major meeting, AIST Tech, is coming to Pittsburgh next year, May 4th through 6th, and we will look forward to seeing you there. Thank you again, Wendy, Alton, our moderators, Tim and Pollyanna. Look forward to the next webinar on the 11th of November, which is available on our website. Thank you all. Have a good day.